For the introduction, so I just have to start the presentation. Actually, it's pretty close, but I'm not officially working for the University of Hamburg, but I'm working for the Center for Applied Nanotechnology. Sounds like a big difference, but in reality, it's just one floor, because we are in the 4th floor and the university is in the 3rd floor. So my boss is Professor Weller, and when I was invited here, I was asked to do a talk about continuous flow synthesis of nanoparticles, and that's exactly what I want to do now. But I don't want to talk only about the possibilities using that technique, but I want to be very honest to you today, so I want to talk about the problems too. But before we will do so, let's start with a few words about the well-known batch procedure. So no matter if you do the batch procedure like hot injection, like it's shown here, or if you do thermal decomposition, you always end up with some kind of a flask, and you will have your nucleation in the flask, and then you will lower the temperature to have the particle growth. And after you have reached the desired particle size, you just cool down to room temperature to obtain the particles. And it sounds pretty easy. And yes, it is pretty easy, to be honest, I think so. And here are a few examples for iron oxide made with this batch procedure. So these are 5 nanometer particles, 15 nanometer particles, 10 nanometer particles, and this works up to around 25 nanometers. So you can easily change the particle size just by varying the reaction conditions. And if you look a little further, so not only on iron oxide, then you find that you can even vary the shape of the particles using the batch procedure. So this here is classical spherical shape, but you can also produce cubic nanoparticles or rod-shaped nanoparticles or even quite long wires or small tetrapods or giant tetrapods. They have an arm length of approximately 250 nanometers. They were all made in batch just by varying the reaction conditions. So you can ask, what about the crystallinity of these particles? So let's check. Let's do a TEM analysis of iron oxide particles we made still using the batch procedure. So to see the crystallinity, we have to increase the magnification so long until we see the crystal lattices of the particles. So we haven't reached the point yet. We can only say, okay, they are obviously spherical, a little faceted on the surface, and rather monodispersed in size. But if we further increase, I would say now you can see the crystal lattices of this particle, and it's really nicely crystalline up to its surface. There's only one crystalline domain. And if you further increase the magnification, you can really check if all atoms are aligned really nicely. So yes, they are. Obviously, it's a quite good method to do particles. So it's obviously, you could ask, why is a new method for the production of nanoparticles needed? Or you could say, why am I wasting your time here? So, to answer this, I would like to show you 2 other movies we did in my lab. And the first one, or both, show the hot injection procedure, so the synthesis of nanoparticles. But to be precise, they not only show the whole synthesis, they show the injection and the very first second afterwards only. So we will only see injection and the first second. So let's start with the 50 milliliter flask. So I'll just stop it for a second. So here you see the flask, 50 milliliter. This is quite usual size for university. So here you have your precursor, you have your stabilizer, your solvent, a magnetic stirrer. Everything's fine. It's heated to nucleation temperature. And here you do see the syringe for the injection. So let's start it. And now you will see my coworker Katarina injecting the second precursor as fast as she can. And you see you get a very strong initial mixing, mainly because of the injection, not so much because of the stirrer. And straight after the injection, the solution is turning brown. This is the nucleation of the particles. And straight afterwards, so we are still in the very first second, still afterwards it's starting to get more dark. So the particles start to grow. And so here you see that I would say during the first second, it's all done. So if the first second goes wrong, you will end up with bad particles. So afterwards, you will just get some particle growth, but you will not influence, or you can influence, but you will not make the size distribution better, maybe just worse. So this was a quite good example. So this yielded really nice particles, but 50 milliliter flask usually gives you something 20, 30 milligrams of particle. This is usually enough. If you only want to know more about the synthesis, but if you want to do some application or further studies, you usually need more. So no problem. Let's take a bigger flask. This time we have a 1 liter flask, and Katerina has to inject the precursor again. But here you see, this time she has to inject much more because it's a bigger flask, a bigger amount. And you see that the mixture during the injection, it's not as good as before. So here there's nearly no mixing, here is nearly no mixing. The injection is not really finished, so she's still doing the injection, but the first nuclei here already started to gain up. And the nucleation here starts here, and here we have an awful lot of gradients in the flask. The nucleation is maybe in some parts it's already finished, in other parts not really started. And now the injection is close to finish. So you really can see that this here has not yielded really good quality particles. So this is a bright size distribution, a very broad size distribution. So in principle, this is not useful for any kind of further experiments. So that's why we think we need something new to improve the reproducibility from batch to batch and to face this upscaling problem. And this is the wish list. So we wanted something which is possible to solve all problems we had. Of course, you always want something which solves every problem you have. So it's suitable for all kinds of nanoparticles, yield nice particles with different sizes, and able to do this very high reproducible and with an increased throughput, and of course with less work. So what we did, we set up a machine which is based on the idea of an ideal plug flow reactor. I don't want to go in detail into that too much because it would take too much time. But what I want to tell you is that, of course, there's always a difference between ideal and reality. So here you see the task we had to face. If you talk about nanoparticle synthesis, you usually talk about very high temperatures. So you have to be very careful about the materials you use. You have to be very aware of the synthesis you use. Usually you have to change it a little bit so that it's suitable for a continuous flow reactor. And of course, you have to find a layout which works very nice. So here, for example, you see the trial of nanoparticle production and continuous flow, and you see that the particles are quite sticky to the surface of the reactor, especially the small ones. So especially those straight after the nucleation tends to stick to the reactor surface, so you have to be very careful about the ligands you use and the temperatures you use and so on. So this is the layout we originally set up, especially for the production of semiconductor quantum dots. And I want to go in detail a little bit about the single components, what we made. So just to tell you, this here is in principle, this is it. So all the chemistry is taking place in here. All the rest are just pumps and vessels and spectrometer and scale. So we had several challenges. So one, for example, is the handling of very sensitive reagents. So to do so, we have very special vessels here, which can be easily equipped with nitrogen and which are very safe, so that we definitely can handle all kinds of toxic and reactive reagents. We have this online degasser unit here to be 100% sure that there is no oxygen present during the synthesis. And what else? You have to be very careful which pumps you select, so you definitely need a pump with a very low flow profile, so it has to be very constant. So of course you don't have to use this one, but HPLC pumps are usually a good choice. About the oven is probably quite problematic because here you do the particle growth, so in here or in here, and the particle growth often needs quite high temperatures. So we have two versions of the growth oven here. This is one. One is made with plastic, so this one goes up to 250 temperature, and the other one is made from titanium, so this one is for really high temperature synthesis. But I would say the most crucial part of the whole system is the microfluidic mixing chamber, because here in this microfluidic mixing chamber we get the nucleation. So this is in principle the part where the nucleation, so the injection takes place, the one we've seen before. It's a very small part, it has only an inner volume of a few microliters, but it mixes really fast and it's heated up to nucleation temperature. So what we get is in principle, we get the nucleation here and we get the growth in here. So we have nucleation and growth at different places, and this is the general idea why we set this up, because we don't have to change the temperature of one component during the synthesis, so everything stays constant. So if you're, I don't know, any of you have worked with microfluidic components yet? Somebody? 1, 2, okay, 3, not very much. If you're interested, I have 3 different microfluidic mixers here with me, so you can come afterwards and take a look at them. So another challenge is the online quality control. Here you can see we do absorption and emission online to check for the particle properties. And another thing, of course, as I told you before, we want to reduce the work, and of course we like to work in the office and not so much in the lab. So what we did is we had to develop a software, and here it is. So this in principle can operate the reactor from all around the world, so it works via internet. So now just a few examples about the particle production we did using this machine. I would start with the cadmium selenide because this is the one it was originally designed for. I will really rush through this, but just to give you an idea about the different influence factors we have. So for example, the flow speed. The flow speed influences the particle diameter a lot, but there's only very, very, very small influence on the size variation of the sample. So this is a very, very good possibility to change the particle size. On the other hand, if we change the nucleation temperature, there's only a tiny influence on the particle diameter, but there's a huge influence on the size distribution of the sample. So obviously, high nucleation temperatures leads to very good quality particles. And on the other side, the last influence factor I want to show you today is the growth temperature. Here you see there's no growth below 120 degrees. And if we increase it further on, we will get here particle growth, so we can influence the size of the particles. And if growth occurs, you can see that the size distribution is getting better. So obviously there's some kind of size focusing effect during the growth, so it's good to use it. But most important, what about the reproducibility? And here you see 3 absorption and emission measurements of cadmium selenide nanoparticles made online. And they are not just made one day, so they are made at different days. And between lot 1 and 2, we produced another kind of particle, and lot number 3 was made by another operator. But I think you can really nicely see how similar absorption and emission look like. And using semiconductor quantum dots, they are very sensitive to the smallest change in size. So you see that we here really have a very nice reproducible way to produce particles, and we were really surprised to see how good this worked. We then further expanded the system for core shell and core shell particles, and for other semiconductor particles as well. So for example, lead sulfide in the IR. But I don't want to show you this, but what I want to show you is another type of particles, so nickel platinum. Here you see the, let's call it the end result after optimization via experimental design. So we like to use experimental design to find the optimal settings to produce a certain size of particle. And here we were looking for very small nickel platinum particles because we wanted to use them as a catalyst. And here you see that they are quite monodispersed, and we were quite pleased with that. We could change the particle size between 2 and 4 nanometers. That was really nice. But now let's talk about iron oxide. So iron oxide, well, you all know this. There are quite a lot of well-established batch synthesis around, which yields from small to quite large amount of particles in the gram scale. But we feel that the reproducibility of the iron oxide synthesis is not really well So you usually end up with a really nice sample. You usually have a very small size variation in your sample, but it's hard to predict what exact size you will produce. So it's really hard to say, today I want to do 16 nanometers. So if you want to do 16 nanometers, you usually have to do several batches until you reach the 60 nanometers. Maybe you get 14, then you get 18, and then the third one you might get your 60 nanometers. So we don't really like that. Another thing is that, of course, the size influences the magnetic behavior. So it is really important to obtain the certain size and we shouldn't forget that there are some cooperative effects if you combine more than one particle. But there's one property which is not mentioned here on that slide, and it makes iron oxide my very special friend. So iron oxide is probably the particle system which is really a nightmare to do in a continuous flow system, and I will show you why in a second. So this here is the setup we used for the iron oxide production. So what we do is we have an iron compound in here, we have oleic acid in here, mix it at room temperature, heat this up to 300 degrees. This forms initial particle. Then we add some N-oxide to oxidize it and heat this up first to 130 and then to 300 degrees. This is more or less similar to a synthesis which is published by Hyung, but we just made some tiny changes to make it possible in a continuous flow. And here you can see a result, so quite nice 10 nanometer particles. So far so good, but there are a lot of problems. So for the iron oxide synthesis, you have to use really high temperatures because you need the high temperatures for the crystallinity of the particle. So you're well above 300 degrees. If you are above 300 degrees, you definitely get problems with most of the material, especially the sealing you need for your continuous flow reactor. Another thing which I personally hate most are the long reaction times, because long reaction times lead to very slow flow rates. And very slow flow rates usually leads to quite broad resident time distribution in your system. So this is not good. And on the other hand, the particles have a lot of time to stick to the surface of the reactor. So what you end up is usually with plugging of your system quite fast. And you can believe me that a plugged continuous flow reactor is not really what you want to have. So this makes much more work than you would do it in the batch synthesis. And there are more problems. For example, the oleic acid tends to decompose at very high temperatures, and this yields to some gas components which arise in your growth oven. And if you get gas in your growth oven, then usually you get an uncontrolled change of the residence time distribution, and this is definitely not what you want to have too. And there are even more problems. So for example, if you use iron oleate as a precursor, this is not really stable. Maybe it looks stable, but it changes the properties over time. So if you do a synthesis straight after you prepared it, it will give another size than you do 2 weeks afterwards. So you definitely have to keep this in mind, and this is quite hard to do reproducible particles. So overall, I have to say that we still use the batch iron oxide particles when we are looking to use them. So we are working on the continuous flow synthesis of the iron oxide, and I will promise you that there will be a continuous flow synthesis one day, but I would say it will still need some time to get there. Just to finish with, I think it's very important to talk a little bit about the phase transfer, because just up until now we just have seen particles which are soluble in organics. But if we want to do some life science application, of course, we need the particles in water. So what we do is we start with our hydrophobic particles, and then we mix it with amphiphilic polymer, add some water, and due to the addition of the water, the polymer forms micelles, and the micelles encapsulate the hydrophobic particles. And to check if this works really well, quantum dots are usually a good choice. And here you see, if we take our water-soluble quantum dots and dilute them, there is nearly no change in quantum yield, so this is a really good sign. We can dilute them down in the picomolar range, and they still have the same quantum yields. So how do we do This encapsulation procedure, I think you already guessed it, it's a continuous flow procedure too, because I think there's not big sense to do or to try to get the best reproducibility in the synthesis and then to end up with a bad reproducibility during the phase transfer. So we do a continuous flow approach here too. What we need is in principle only a microfluidic mixing chamber, like I have here. And here we add the water and the particles with the polymer so that the micelles are formed within this mixing chamber. And let's check the reproducibility of this. So here you can see the result of 6 different batches of encapsulated particles, and you can see that size and size distribution measured by DLS is the same all the time, so we are really happy again with the reproducibility of that system. But if you look here at the TEM image, you can see the micelles and you can see the particles. If you look really close, I hope you can see it, you will find that most of the micelles contain just one particle. And that's exactly how it was designed, because it was designed for quantum dots, and quantum dots need to be encapsulated as single particles. But if you look really close, you might find that there are several, really close, oh here's one, that there are several micelles which contain more than one. So usually 2 of a very small amount contain 3 particles. So we had the question, is it possible to change the system to yield clustered particles in the micelle? And yes, it is. So we tried it with iron oxide particles, and what we did is we changed the polymer to particle ratio, and this is very important, we changed the mixing behavior too. So we had to change the flow speed, we had to change the mixer a little bit, and what we end up is with the possibility to do single encapsulated particles, small, medium, or large micelles, which are all filled with iron oxide particles, and they are in the size between 30 nanometers for single encapsulated particles and around 200 nanometer for the large clusters in between. So this is really interesting. If you do MRI, for example, though, you can increase the R2 value from approximately 50 to something around 400 to 500. So this has a huge influence on the behavior of these particles. But what about the behavior of these clusters in MPI? So I wanted to show you at least one Mph measurement today. So we went to Mr. Kuhlmann, who made the talk yesterday, and what we did is we measured the samples in hexane and single encapsulated samples, and you see that there is more or less no real good result. It looks like the blank, but if we take the micelles here, which are formed all with the particles, so approximately a size of 170 nanometers, so quite a lot of them, you see that there's some kind of change in the MPS measurements. So these are really very raw results. So I'm not quite sure about them. We definitely have to repeat them, but maybe it looks like if there is an influence if you lose the clusters. So in the end, I would like to thank all the people here on this slide, especially my particle development team. You can see them here on this picture. And of course, Mr. Kuhlmann for the MPS measurements. And I would like to end with another video just to show you what happens if two, so if two gold particles get together very close in the TEM, it's nothing to do with MPS, it's just for your fun and for mine. So it's without heating, it's just caused due to the excitation in the TEM.
Is that real time?
Yeah. So that's it.